Let's continue on this journey, shall we? We're going to keep going into the depths of integration. Formally, integration is the inverse of differentiation, right? We're undoing derivatives. That's what we're doing here. So when we take the indefinite integral with respect to x of f prime, we're saying the derivative of what got us f prime? Well, that'd be the derivative of f plus some unknown constant, right? We don't know what the constant is. You can't guarantee that it's just f of x. It could be plus some number because the derivative of c is 0. So to check your answer, you take the derivative of this, and we should get back what is called the integrand, this piece here, back. Sure enough, the derivative of that is f prime plus 0, or f prime. So what if we did it the other way? What if we took the derivative of this? Well, this would be saying the derivative of what got me f of x, and then take the derivative of that thing. So you're undoing each other. So that would equal out to just f of x. That's all. No plus c, because this would have given you something with a plus c in it. That. Call it like capital F of x. Let's say that's the antiderivative of f. Well, if we take the derivative of this, we'll get back to f, and the c will fade away. Nice. So I like to think of it in these terms. In terms of velocity and position, right? We like to think of those as levels. Position, take a derivative of velocity. You are given the velocity, and you need to work backwards to find the position. That's it. That's all this is. So we're going to go over some of the major rules now, and we're going to use that inverse idea in all of this. Oh yeah. And the screen got a little bit narrower there, so you got some nice blue on the sides there. Isn't that sweet? Oh, very sweet. Okay, so the derivative of any constant, we know that's 0. Therefore, if we're going backwards, what would be the integral then of 0 with respect to x? Well, if the derivative of k is 0, then the integral of 0 is some constant k, right? We often would use just c for that constant integration. We'll use k here. That's it. And you check it by saying the derivative of this gives me 0. Check. The derivative of k times x, any constant times x, is k, right? Like if it was 3 times x, the derivative would be 3. So then what is the integral of k with respect to x? Well, the indefinite integral of that would be, we're going backwards, k times x plus some unknown constant c. That's it. We're just backing up. The derivative of k times f of x, again, the constant's just chilling there. That'd be k times f prime of x. So in other words, if you had 3x squared, the 3's hanging out, and you take the derivative of x squared. So we're then looking at the opposite way. We're saying, okay, so what's the integral of k times f prime of x dx? Well, we'd be going backwards. The k essentially is just hanging out, and the integral of f prime is f, because the derivative of f of x is f prime, and of course you need the plus c. So just going through some major rules. This is the big one. Let's put a little asterisk there. This one's huge. You could use it all the time. Get good at it. It's the power rule. The derivative of x to the n, we know, is n times x to the n minus 1. So then, pray tell, what is the integral, the indefinite integral of x to the n dx? So we now go backwards. Instead of subtracting 1 and multiplying by the n that was up here, we're going to do the opposite. We're going to add 1 and divide by that number right there. And of course, add c. This is the big one. That is the exact inverse. Add 1 and divide instead of subtract 1 and multiply. All right, that is the big power rule right there. If you take the derivative of this, you'll get back x to the n. All right, the derivative of sine x, we know that one. It's cosine of x. So therefore, if we go backwards, the integral of cosine of x with respect to x is sine, right? That would be going backwards. And of course, you have plus c. Okay, on to the next one. The derivative of cosine we know is minus sine. So I'm going to botch this one up a little bit on purpose. So then what's the integral of sine of x? Well, sine of x would therefore be minus cosine. Why is antiderivative minus cosine? Well, because the derivative of cosine is negative sine. We have a positive sign here, and a negative times a negative is a positive. The derivative of tan we know is secant squared of x. Therefore, if I'm given the integral of secant squared x dx, I'm saying the derivative of what gives me secant squared? Oh, the derivative of tan gives me secant squared. So it'd be tan x plus c. Know it going backwards. Derivative of cotan is minus cosecant squared of x. So if I have the integral, we're just going to do a positive of cosecant squared x dx. That's going to be minus cotan x. Again, That's to account for the negative here in the derivative, which we didn't have here in the integrand. The derivative of secant x is secant x tangent x. Nice. So if you're given the integral of secant x tangent x, a dx, what's that going to equal out to? Well, the derivative of what gives me that? Secant x plus c. And again, you can take the derivatives of any of these and you'll get back your integrand. Last but certainly not least, the derivative of cosecant x is minus cosecant x cotangent x. That's the derivative. So the integral of cosecant x cotangent x dx, what's that going to be? Let's think about that one. Well, the antiderivative of that, the integral, is going to be minus cosecant x. Again, to account for no minus being here, as it was there. So we get minus cosecant x plus c. All right, that's it. I just wanted to show you in this video the basic rules and the idea of the inverse there. What we're going to do in the next video is we're going to put these rules to practice, but know your rules well, forwards and backwards, and understand that the derivatives of all of these answers here would get us back to all these integrands. And we established these rules by just knowing the derivatives. So we went forwards and then we went backwards. That was fun.